morning to all participants. Now, today we will see a lecture from Professor Stacy McGaugh uh, uh, from University of Case Western University in US. Uh, the title will be The Scaling Relations in Galaxies. But before, I will read the Professor McGaugh CV, a short CV. Maybe I will. Okay. Professor Stacy McGaugh, now a professor in the Department of Astronomy of Case Western Reserve University from 2012. He is a chair of Department of Astronomy from 2015. He started education from Massachusetts Institute of Technology in 1985 from physics, and then PhD in astronomy from University of Michigan. His research are about low surface brightness galaxies, galaxy formation and evolution, test of dark matter and alternative hypothesis. Okay, can you hear me all?
Yes.
Yeah. His research interests are low surface brightness galaxies, galaxy formation and evolutions, test of dark matter and alternative hypothesis, measurement and cosmological parameter. But I have to give you a statement that today's lectures is recorded because Professor McGaugh cannot attend directly in the synchronous lectures. Now we will play you his recorded lectures, and all the questions will be kept and sent to Professor McGaugh. You can write your questions in the chat, and we'll send you. If few questions I can answer, I will give you the answer from this lecture. But most of them I will send to Professor McGaugh so he can send you the answer in written versions. Okay. Okay, Anton. Please play
Okay.
the recorded version.
Okay. Just wait a minute.
Hello, I am Stacy McGaugh, Professor of Astronomy at Case Western Reserve University. It's a pleasure to be here with you today, if only in a virtual capacity. The organizers have asked me to speak about scaling relations in galaxies, which is a subject near and dear to my heart and many of ours, and has implications for the natures of the dark matter, or more generally, the mass discrepancy problem in the universe. This is UGC 2885. It is an example of what we're trying to understand. A big, beautiful spiral galaxy. This is one of the most massive galaxies in the local universe. And I'm going to talk about two broad categories of scaling relations. Photometric scaling relations, which have a lot of scatter, and kinematic scaling relations, which have rather little scatter. There is what I hope is a digestible summary of the latter in my presentation last year to the IAU meeting in Shanghai, when we could actually travel in that archive location. So of course, remember the Hubble tuning fork morphology diagram, where we distinguish between elliptical galaxies and spirals. Typically, we think of spirals as having an increasing disk fraction, whereas bulges are more and more dominant as we go from late to early type spirals and on into pure pressure-supported elliptical systems. Just some quick examples. NGC 3379 is a typical elliptical galaxy. It's basically a 3D blob of stars. It is pressure supported. The orbits of stars are arranged all over the place. They have no preferred plane, and you just basically have this sort of chaotic dispersion of stars going every which way, which fill out this 3D blob that's ellipsoidal in shape, and we see that projected on the sky. This condition is called dynamically hot, where there's a lot more kinetic energy in that pressure of motion, the velocity dispersion, than there is in organized rotational motion. On the right, we have two examples of spiral galaxies. NGC 628 seen face on, and NGC 891 seen edge on. These are thin, rotationally supported disk galaxies. The motions of the stars are largely organized into the same plane, orbiting in the same direction, with more or less circular orbits. There is some velocity dispersion, but that is small compared to the circular speed. This condition is called dynamically cold, and it's something that's a little hard to maintain in the universe. So the fact that there are so many spiral galaxies is immediately an interesting point, and was in fact one of the original reasons to invoke dark matter, was to stabilize these rotationally supported disks. That's something we need to maintain in any explanation going forward. At the tail end of the Hubble sequence, there are many dwarf and low surface brightness galaxies. Those are not necessarily interchangeable terms. Most people use a dwarf galaxy to mean low mass. I use low surface brightness, or LSB here, to mean diffuse, spread out. And if that diffuse galaxy is spread out over a large enough area, then the total integrated mass need not be small. Nevertheless, there is a correlation there, and that dwarf galaxies do tend to be low surface brightness. We've had to sort of add classes on to the end of the original Hubble sequence in order to account for those things. As we survey deeper and deeper, we find more and more of these low mass and low surface brightness galaxies, which tend to have later type and even irregular morphologies. I do want to make the distinction here between early type galaxies, as some people call them, basically the elliptical galaxies, and late type galaxies, LTGs as they're sometimes referred to, which I'm going to use to include everything that rotates. And within those rotational classes of galaxies, I mean early type spirals, late type spirals, and irregulars. So there's already ample grounds for confusion, because sometimes spirals, which are late type galaxies, can be early types, like SA. So we have early type spirals, which are late type galaxies. I'm sorry, I didn't make up this terminology. But it's important to realize that these things exist over an enormous range of mass, size, surface brightness, gas fraction, star formation rate, and morphology is not really indicative of any of those things. There are some correlations, as you'll see, but they're messy. Now, we can quantify morphology in a number of ways, the most basic of which is to do surface photometry. Here's an example shown for elliptical galaxies. The image at top left is just the raw image from 2-mass of an elliptical galaxy, to which isophotons have been fit in the lower left panel, in this case by Jim Schomburg using his Archangel package, which is, in my opinion, the best thing out there if you want to do this kind of work. But there are many things that are adequate, and what they provide you is an azimuthally averaged surface brightness as a function of ring radius. So each of those isophotes in the lower left image corresponds to a ring. You can measure the average surface brightness in that ring and plot that as a function of radius. And if you like, fit some kind of typical profile to it. For elliptical galaxies, common choice is the divocular or the 1/4 profile. Or if you're willing to add a third parameter, you can plot a Thursich profile. For elliptical galaxies, there are good empirical templates. They are not as well known because there's not a simple formula that you can write down, but they're a little more accurate in actually describing the data because they are based on the data. And for elliptical galaxies, the profile shape is found to vary systematically with luminosity, as you can see in the left panel, with the top line being very bright elliptical galaxies and then ranging down to lower luminosity galaxies. Those same lines are reproduced on the right to show you how they compare to the analytic divocular profile, which would be a straight line in that are the 1/4 radius on the right. And so that is a decent approximation of the luminosity profile of elliptical galaxies, but it's not perfect, and real galaxies tend to deviate from that at both the inner and the outer isophotes. For late type galaxies, things that rotate, typically have an exponential profile. And here I'm going to talk a lot about high and low surface brightness galaxies, so I want to graphically illustrate that difference. What you see here are sky survey images of a nice high surface brightness spiral at top, a low surface brightness galaxy at bottom. The top you see right away and put it in your catalog. The bottom you see, okay, maybe there's a smudge there, maybe it's real, maybe it's not, and maybe you do not include it in your catalog. That is a real smudge. We can zoom in there and, okay, they're comparable in diameter once we turn up the gain. So these are much higher signal to noise, higher contrast images. The low surface brightness galaxy at bottom, the contrast has been turned way up so that you can see that in fact the diameter is comparable. The distances of these pairs are about the same, which is why I chose them to illustrate that in this case it's not the size that's different, it's the surface brightness. It's the difference in how closely packed or diffusely spread the stars are within the galaxy. We can again fit ellipses and plot the surface brightness profile. That is reasonably well fit with the exponential profile, the formula for which is given there and is shown as the red line. It's characterized by a central surface brightness, sigma naught, and a slope, r sub d. Those are sort of a bare minimum number of parameters you need to describe galaxies like this, because it's not just the total luminosity or equivalently mass, it's also how that mass in stars is spread around. So this is an example of that central surface brightness against that scale length for many galaxies. Each point now is one galaxy, and you can see that galaxies live all over this plane up to maximums in both luminosity and surface brightness. The maximum in luminosity is a bit more than L star, of course, and galaxies simply don't get much bigger than that. The line of constant L star is from the Schechter function is shown as a dotted line. There also seems to be an upper limit to the disk central surface brightness that is shown as another dotted line up at the top, sigma dagger, and galaxies simply don't get a lot more higher surface brightness than that. On the lower ends, both in size, luminosity, and surface brightness, there's really no limit except what the limits of our observations show us. And whenever we push those harder, we always find lower surface brightness things. And that continues today with the discovery of ultra diffuse galaxies and so forth. Now, there are enormous selection effects that afflict our ability to see these things. This is a simple calculation illustrating the volume that a survey probes as a function of both the luminosity of a galaxy and its surface brightness. So, of course, as things get fainter and less luminous, then the inverse square law means we cannot see them as far away, and so the volume probed falls off as a strong function of that intrinsic luminosity. The same thing happens for surface brightness. Even at a fixed luminosity, if all of that surface brightness is hidden below a very faint isophote, then you can still barely see them. So you have to carefully take account of this in order to correct what one sees to what is really going on in the universe. So to illustrate that, here's the raw number of galaxies in Sloan. I think it was data release 7 when I made this. Just a raw number of galaxies as a function of mass. And you can see there's a very clear peak, a little short of 10 to the 11 solar masses. The high mass side of this is the intrinsic cutoff in the distribution. If there were really massive galaxies, they'd be easy to see. At some point, galaxies simply become very rare. You don't see a lot of super high mass galaxies, and so you get that cutoff at the high mass end. The turn down at low masses is purely a selection effect just from the difficulty of seeing fainter sources. And so what you need to do is apply some measure of the selection function of your survey to correct for that volume difference in order to get to the intrinsic number. So here I've overplotted the so if we correct for the volume sampled, we take that very small number of observed galaxies at low mass and greatly magnify them in order to show the total intrinsic number in terms of space density. So always bear in mind that the raw number of galaxy counts in any survey is always biased to the brightest, most easily seen thing. And there are a lot more small things out there that we would like to keep a fair accounting of. So to give an example of how strong this is, one can go out and make some kind of magnitude complete sample, and yet you will have almost all bright galaxies, because that does not include any kind of volume correction. It's just complete down to whatever magnitude you have. So here's a plot of scale length against stellar mass for a large sample of spiral galaxies. You can see how they're distributed in the plane. You can imagine there's some scaling relation between size and mass. But if you go out and look harder, you can find many examples of other galaxies that are lower mass, lower surface brightness, and live all over this plane. So here the colors split up between early type spirals and late type spirals, with the transition being around SC or SCD. There is no perfect correlation with morphology, but in general, the early type spirals, SA, SB, SC, are massive and live at higher surface brightnesses, whereas the later types are lower mass, lower surface brightness, and more gas rich, as we'll see. So comparing to that magnitude limited sample, you can see that it has lots and lots and lots of early type spirals and practically none of the later type spirals that are very common intrinsically in the universe, but we're simply missing because that's what happens when you only concentrate on what you see from standard surveys. Just to give you some feel for what kind of galaxies live where, the most massive galaxy we saw before, UGC 2885, resides right there, is reasonably big in scale length and high mass. and there are relatively few other spirals that big. Our own Milky Way resides right in the middle of that blob. It's a fairly typical, roughly L-star spiral galaxy, a little on the compact side of the distribution, depending on who you ask. But down here, there's a whole universe of dwarf and low surface brightness galaxies, have very loose spiral structure, if not outright irregular, and live down here, low surface brightness being here, high surface brightness being there. So now what you would call a scaling relation depends on what you choose to fit. So if you had only known about those bright galaxies, you would fit some relation here, and that would fail to extrapolate to these things here. So you could now fit a different relation to the entire sample and call that the size-mass relation. But remember, this is incomplete. These are a better sample of the universe, but there's no formal completeness to it. You might also note, okay, well, there seems to be two different clumps here, the early types and the late types, so maybe we should fit a separate scaling relation to each of those, and then you'll get a different size-mass relation for each of those in turn. That's all fine, but the answer you get depends on what choices you make. So it's not just a matter of the data, but it's also how you choose to go about fitting it. And remember, this is incomplete, so maybe things do something different if we keep finding lower and lower mass galaxies. It also depends on how you define these quantities. So this is the baryonic mass rather than the stellar mass, and a scale length that's defined by its the dynamics rather than just the photometric scale length. So basically how compact the mass is. So galaxies with big bulges are now very small because most of the stellar mass is packed into a very compact bulge. Whereas these later type galaxies have very extended gas distributions, and so they're pretty big. And so on this diagram, you wouldn't say really there's any correlation at all. The difference between high mass galaxies and low mass galaxies is not size, but surface density. These things are high surface density, these things are low surface density. It's a matter of compactness. So it's quite a bit different what you see here and what you see here. So again, the scaling relation we would derive depends on how we see it. This is very common because you can observe both the scale length and luminosity, turn that into a stellar mass by some prescription within the framework of one survey. So if you go out and do Sloan, then this is what's readily accessible to you. The dynamical scale length, you have to measure some sort of rotation curve. The baryonic mass, you need to add the gas as well as the stars. So there's a different requirement on the data. So I'm going to decline to fit a scaling relation to these things because it's specific to the choice that one makes. In general, what you really want to know is the bivariate distribution of size and surface brightness. So this is an old example from de Jong and Lacey, where we're plotting the effective surface brightness as a function of the effective radius, and then the density of those squares tells you how many galaxies there are there. So you want to know the intrinsic volume number density of galaxies as a function of both the surface brightness and the size. And you see again, galaxies are all over the place down to the limits of selection. Now expanding our discussion to include early type galaxies as well as late types. So now we're plotting the effective radius, that is the half-light radius, as a function of stellar mass for ellipticals in gray, as well as rotating galaxies in color. I've expanded that as much as I can, and you can see, at least in terms of half-light radius, elliptical galaxies cover more or less the same range as late-type galaxies. even though they have a very different profile type. So this would change if we chose a different definition of radius, but at least roughly speaking, galaxies are sort of this size. And again, there's no limit on the size that one can get to, and this lines show lines of constant surface density. So low surface brightness here is one of the lowest things known, due to my colleague Chris Mijos and his student Chris Carr. On the other hand, some of the highest surface brightness things lie along that line. So there's a large range in between. There is a huge intrinsic variation in size and surface brightness with mass. It's not like there's just one scaling relation that if you know the mass of a galaxy, you know its size and its surface brightness. The variation here is real. The uncertainties are of order the size of the points or smaller. Galaxies are not just made of stars. So far we've only talked about what you can see in the optical. They're different at different wavelengths. So here's one spiral galaxy, NGC 6946, the optical image on the left, a near infrared image on the right, so that's sort of JH and K, whereas the other is BV and R. And those are similar morphologically, but not identical. And then on the right, there is the atomic gas is mapped by the 21 centimeter line. And these are all to the same physical scale. So you can see that the gas is much more extended in radius than is the stars. And this is fairly typical of spiral galaxies, and even more so for late type spirals and dwarf irregulars. So to have a complete view of a galaxy as a physical object, you really need to know something about its interstellar medium as well as its stellar content, stars and gas. So very crudely, here's just the global gas mass against the stellar mass for a whole bunch of galaxies. The same color coding by type for galaxies for which we have a lot of data from the SPARC database put together by Federico Lelli. You can see here that a lot of late type galaxies have more gas than they have stars. That diagonal line is the line of equality. So anything above that has more gas than stars. Usually we think of spiral galaxies as having small gas fractions, 10 or 20%. And that's true for the early type galaxies, those red points at top right. But for lower mass galaxies, it's actually more common to have more of the mass in the form of gas than in the form of stars. And so it's easy to speculate that the difference in morphology has to do with the two fluid instability, and you only get really nicely formed spiral arms when stars start to dominate the mass budget. I've also included early types here as squares and upper limits, triangles pointing down from the Atlas 3D survey, these data from Sarah et al. So sometimes there is gas detected in early type galaxies, as zeros especially, and those tend to overlap with some of the early type spirals. But then there are also a lot of upper limits that are well below that in terms of gas mass. And again, you can see the hard edge at about 10 to the 10 solar masses, below which the survey simply doesn't have any galaxies. It's not that they're not there, they're just not readily found and included in the study. Another commonly discussed scaling relation is the so-called star-forming main sequence. This is a plot of the star formation rate against the stellar mass. And so here I've cobbled together data from many different sources. Oftentimes you'll see this discussed in the literature only for bright spirals, the early type spirals, those red points, and you get all sorts of different slopes. And again, this is just a result of fitting a different range to the data. What do you have there? So if you look at those red points, you would fit a fairly shallow slope But if you go to all the other colored points, which is common for dwarf irregulars, then you get a slope of about 1. It's along a line of basically what a galaxy would do if it had a, on average, constant star formation rate over a Hubble time, as it must, because these axes are not physically independent. The stellar mass is, of course, the integral of the star formation rate. So a galaxy cannot exist above the dashed line for very long without creating a whole lot of stars and moving to the right. So starbursts must be rare in this kind of diagram, and you see a couple examples there, but by and large, galaxies have to lie along that line until they exhaust their gas supply, at which time their stellar mass is made, they stop forming stars, and so they would start to evolve downwards in this diagram, which you can see the beginning of for the weary giants, as I call them here, the early type spirals, and going on down to the red and dead early type galaxies, which have basically stopped forming stars or doing so at a very, very low rate compared to the past history. Whereas for dwarf galaxies, they're just driving along, forming stars, and will continue to do so for many Hubble times. Note that the same morphology appears in both this diagram of gas mass against stellar mass and star formation rate against stellar mass. So you could sort of infer the one from the other. This is at least independent, but basically when galaxies still have a lot of gas, they continue to make stars at a roughly constant rate, on average, with lots of stochastic ups and downs along the way, but over billions of years, it's a roughly average rate. And as you get to the end of that gas supply, then galaxies evolve downwards in these diagrams with their star formation rates declining as they use up their fuel. So now I will give you some numerical relations for scaling relations. Gas mass against stellar mass, number 1, all these are log-log plots to which I've just fit a straight line to the blue points only. So again, it still matters what range of data you choose to do, and sometimes that extrapolates better than others. So the fit is shown as a solid line. The extrapolation of that fit is a dotted line, and that doesn't do too well in the gas mass stellar mass relation because you really are reaching the end for the red points compared to the blue points, using up that gas. Whereas it works better for the star-forming main sequence or the global equivalent of the Kinnickett-Schmidt relation in the third panel there, or why use just gas mass or stellar mass, why not most baryonic mass? That seems to form a pretty good scaling relations, and you can fit lines and put numbers to it. And if you want to know one quantity from another, you can use one of these relations to at least guesstimate what the other quantity would be, noting that there's a lot of intrinsic scatter here, so you're going to be off by roughly 0.3, 0.4 dex on average, depending on which relation you're talking about. Now, gas comes in different forms. Most of the mass of gas in galaxies is in the form of atomic gas that we detect in neutral hydrogen through the 21 centimeter line. Most of the stars are forming in molecular gas, which is usually detected in CO or some other molecular band. Those observations are often hard to come by, so the scaling relations can get useful in order to get from one to another when you need to know such things. So roughly speaking, that star forming main sequence is just constant. So basically there's a specific star formation rate of a few times 10 to the minus 11 per year that converts the stellar mass into an equivalent star formation rate. The star formation rate also seems to scale with the amount of molecular gas available. It's basically, to a good approximation, the star formation efficiency is roughly constant, as pointed out by Leroy et al. A long time ago. But that lets you map from one measurement to another. So for example, On the left, you have the star formation rate. On the right, you have the molecular gas mass that is inferred to sustain that star formation rate. And that goes along well with what you would have predicted from putting those scaling relations together, i.e. that red line is about 7%. That is, the molecular mass is about 7% of the stellar mass. There is considerable uncertainty in the absolute calibration. Maybe it's 10%, maybe it's 5%, but somewhere in there, there's a rough scaling between stellar mass and molecular gas mass. So if you needed to make a guess for that, for these galaxies, which on the right are poses open squares, because the molecular gas has not been detected there. It's a hard observational job, but there is star formation that's detected, and so you can infer about how much molecular gas mass you need to sustain that star formation. Note that the different kinds of gas do not really correlate well with each other. On the left here is the molecular gas mass from the X gas survey as a function of the atomic gas mass. And it's pretty much a scatter diagram. The dotted line is the line of equality where the molecular and H1 mass are equal. That's at the top edge of the distribution. There are a few galaxies with more molecular gas than atomic gas, but in general it's the other way around, that the atomic gas greatly outweighs the molecular gas mass, but they're not well correlated at all. You're actually better off guessing at the molecular gas mass from the stellar mass than you are from the atomic gas mass. There is also a relation between the mass and metallicity of a galaxy. This has a tremendous amount of scatter and also has some second parameter dependence on the gas fraction or maybe the star formation rate. But it's something to be aware exists. I've given one example here just to be specific, but there are many attempts to calibrate this in the literature. One thing that is helpful for is that you can use it to, again, relate the hydrogen fraction to the stellar mass. So you can measure the atomic gas mass. Sometimes you can measure the molecular gas mass, sometimes not, and you need a scaling relation. And then you want to say what's the total amount of gas associated with that when I account for helium and metals. And of course you can have at the low end primordial abundance. After some evolution, it's somewhat different from that. So one can put all these together and estimate what the variation in the hydrogen fraction is. So I've given that on the right. X is the hydrogen mass fraction as a function of stellar mass. It's basically the primordial value of 3/4 minus a little bit for the evolving metal content of galaxies. That's a very weak function. So you can see that the inverse of X ranges from 1.34, just a little more than primordial for a dwarf galaxy, up to about 1.4 for a Milky Way mass galaxy. In some applications, you want to know that, even though it's fairly persnickety. Now, those photometric scaling relations are pretty weak. They have a lot of intrinsic scatter and variation from type to type. I'm going to talk now about kinematic scaling relations, for which things are actually a lot more well defined in the sense that the relations are strong with little intrinsic scatter. Then there are a number that one can identify, and I will go through those in order, starting with flat rotation curves. Now, rotation curves we derive from velocity fields like this one. This is also NGC 6946 from the Things survey, where you can see the different colors refer to the different Doppler shifts within the galaxy. You can fit a tilted ring model to this. Again, you're fitting ellipses in the plane of the sky. And for each ring of the ellipse, you look at the variation of Doppler velocities along the azimuth. That's shown in the bottom right corner. So for each ring, you can fit your best sinusoid, and that corresponds to the circular velocity once you've taken out the redshift of the whole system. And if there are any strong non-circular motions, then they will show up as deviations from that pure cosine theta form. So basically, we take that velocity field and do a form of data reduction to go from that two-dimensional image to the one-dimensional rotation curve. And when you do that, you find that rotation curves are flat at large radii. They have some detailed shape at small radii, and we'll talk about that in some detail. But basically, when you get out far enough, they flatten out. And that is the rule, not the exception, as was shown some time ago now by Vera Rubin and independently by Albert Bosma and others using completely different methods, optical telescopes with long slits in the case of Rubin, and radio interferometry like we just discussed in the case of Bosma. And what you see here are some rotation curves from one of Rubin's papers showing that over and over and over again, rotation curves are approximately flat and maintain that flatness way, way far out. And so that's what leads to the inference of dark matter. To do that right, one wants to do a proper accounting for the stuff we can see, the baryons in the stellar disk, the bulge, the gas. And we can use those images that I showed you previously to compute what the rotation curve should be, would be, if those were the only mass components present. And that's labeled here as a black line labeled baryons. And the difference between that and the actual rotation is what leads us to infer that there's something else going on. A few words about mass modeling. To do this right, you need a good image of both the stellar mass distribution and the gas mass distribution. You can numerically solve the Poisson equation to get what the distribution of radial forces associated with that mass component are. And then separately, one can look at the actual rotation curve. And we'll talk a lot about this in terms of acceleration. So on the one hand, G bar is the predicted acceleration from what you see. Basically, if all the mass that meets the eye was all that's there, the only thing that's going on is Newtonian gravity, then the G bar would be the equivalent to the observed centripetal acceleration, G obs, which you get straight from the rotation curve as v squared over r. That's the actual centripetal acceleration of the total gravitational potential. And those two things are different, which is why we have a problem. So here's an example in practice, a low surface brightness galaxy with a bit of a central light concentration. So the exponential fit, that blue line, does not account for everything that's going on there. And so it's really not good enough to just sort of analytically assume an exponential disk and work through things. You really need to do the numerical solution as taught to us by Benny and Tremaine. To give an example of how badly wrong this can go, Jerry Selwood gives some examples here. On the left, there's a few examples of surface brightness profiles that you might have. The dashed line is a pure exponential, and then the solid lines are deviations from that, one with a central concentration rather similar to the galaxy, the real galaxy we just looked at, another with a depression towards the center, and those map to very different rotation curves. That dashed line has the smooth shape that you can solve for analytically, as Ken Freeman did 50 years ago. But those other mass distributions predict different shape rotation curves, and the difference is not subtle. So to account for that properly and be able to separate out what is luminous matter from what is dark matter, you have to solve this numerically to do it right. And the exponential assumption is just not adequate. Another unavoidable astrophysical uncertainty is the mass to light ratio of the stars. What we observe is the distribution of starlight. What we want to know is the distribution of the stellar mass that produces that light. It turns out that the best way of converting between those is in the near infrared at about 2 microns or 3 microns. So for the purposes of this talk, I will use the mass to light ratios on the right for the 3.6 micron band of Spitzer Space Telescope observations. I could justify that choice at great length, but I don't have time to do that, so I will simply use that as the simplest way of relating the observed light distribution to our best guess for the stellar mass distribution. Basically, take that same number for all galaxies. In detail, one, of course, expects that there's going to be at least scatter in that relation and maybe some color dependence as well. But for these near-infrared wavelengths, both of those effects should be small. So after flat rotation curves, the second thing on the list is what's known as Rinzow's rule, after Rinzò-Sanchisi. I think it maybe should be Sanchisi's law because it's a very well reproduced thing that should be more widely appreciated than it seems to be. And what Rinzò said is that for every feature in the luminosity profile, there's a corresponding feature in the rotation curve and vice versa. So the light distribution and the mass distribution as traced by the rotation curve are coupled. Here's an example from NGC 6946. That central bulge component only contains about 6% of the total stellar mass, and it gives you that red dash dotted line for a predicted rotation curve. And for the most part, it doesn't contribute, but it's a very compact mass component, and V squared scales as GM over R, so even though the mass is a small fraction of the total, it's compact into a small radius, and so it leaves a mark on the total rotation curve down at small radii. And that kind of feature is reproduced over and over again, which is what Rinzò noticed all during his career and summed up in that one sentence. The thing that confused us both when we started exploring low surface brightness galaxies was that the same rule holds. Here's a fairly easy to see example. It's more dramatic than most, but there is a dip in the gas distribution of this galaxy, and that is reflected in the overall rotation curve. And you can even see the difference from one side to the other. Most of the effect is asymmetry that's on one side of the galaxy, and you can see the difference in the velocity fields on one side and the other. So again, what you see is related to what you get when you see a feature in the mass distribution of the baryons, in this case the gas rather than the stars. You see that reflected in the rotation curve. This is a little harder to understand than the previous version. Here in NGC 6946, the bulge, though compact, is the dominant mass component in that inner radii, so it makes sense that it leaves a mark. In this case, the gas is not the dominant mass component. It dominates over the stellar disk, but the dark matter should outweigh it by a lot. And so you wouldn't really think the dark matter would show the same feature. This is a feature in the gas, not in the dark matter, and yet there it is. Now, this is a general rule. As I say, the detailed shape of the rotation curve follows from the observed distribution of the luminous mass distribution. Not precisely as Newton predicts, but there is a clear correlation. We've known this for a long time, so on the top right is a figure I made illustrating this for a review 8 years ago now, where you could already see that there was sort of this rainbow distribution from low surface brightness galaxies, the blues and purples down at the bottom, up to the reds and yellows of high surface brightness galaxies. Now at the time, what we had were optical data, and we made our best guess with population synthesis models. And you can see a clear trend in the color, but there's also a lot of mixing and matching of colors, and that's just from the scatter in the mass to light ratio. More recently, we've been able to get a lot of near-infrared data. That's what's shown in the bottom right corner, and using that as the measure of stellar surface density, we wind up with an almost perfect rainbow. That is, the low surface brightness things have slowly rising rotation curves. The high surface brightness things rise very rapidly and then flatten out, or even fall a bit before they flatten out. And you can see that there's just an almost perfect trend that the scatter in mass to light ratio is much smaller. And so you can see by eye already that what I asserted to you about stellar population mass to light ratios has to be pretty close to true, or else we'd get a lot of mixing of the colors there. Now, a third and really important scaling relation is the Tully-Fisher relation. The amplitude of the flat rotation speed correlates with the mass of a galaxy. So here are some rotation curves. You can see they all flatten out, corresponding pictures of galaxies. The big ones spin fast, the small ones rotate slow. And this was first noticed by Tully and Fisher, with their original diagram reproduced there. And what they're plotting is the luminosity and the line width, which are both proxies for more important fundamental problems, basically mass and rotation speed. So here is that plot for galaxies with resolved rotation curves, stellar mass on the left against the flat rotation speed measured from a resolved rotation curve. And on the right, the same rotation speed plotted against baryonic mass, which is the sum of stars and gas. I've also made the distinction between higher and lower quality data. The higher quality data have distances known to at least 20% accuracy and have V-flat measured by at least 3 points that are within 5% of each other. Some galaxies are not measured far enough out to really clearly see that. And those are the gray points. And you can see there's a big difference in the scatter between the good data and the bad data. Right now, there are lots of papers claiming that there's more scatter than this or that. That is entirely a matter of data quality. If you exert any sort of sensible data quality control, then the scatter goes way down. The other thing you notice looking from left to right is that on the left, the relation bends. It starts out more or less as a linear power law in log-log space, but then it sort of tails off from the best fit line that's there on the right, and that is entirely because the lower mass galaxies are made more of gas than of stars. Hence the need for this baryonic mass Tully-Fisher relation. If you add in the mass, then that restores a linear relation over 4 or 5 decks in mass. So whatever the physics underpinning this relation is, doesn't care whether the baryonic mass is in the form of stars or gas, but it does care quite a bit about how much mass there is. So there's a very tight scaling relation between baryonic mass and the flat rotation speed. It is, in fact, consistent with being a power law of slope 4, with some normalization that you can just fit to the data. And if you go through the error abundances, you can work out that the intrinsic scatter is very small. You can only put an upper limit on it of about 1/10 of a dex. And most of that is what you expect for scatter in the mass to light ratios. So this is a very tight relation indeed. That makes it useful in all sorts of ways. You can estimate a galaxy's mass from its rotation speed or vice versa, or with well-measured distances. You could use it as a distance indicator. Of course, Tully-Fisher has been used a lot for that. Here we have applied it to galaxies with well-resolved rotation curves as opposed to just line widths. The calibration is on the right, using both distances measured through the tip of the red giant branch method and through Cepheids from our own work and from those of Photometry et al. And that all is very consistent. The Cepheids give you the same scale as the tip of the red giant branch. Their measurements give you the same calibration as our measurements within the errors. And the slope is 3.95 plus or minus 0.16, i.e. it's 4 to within the uncertainties. We can then go out and apply that to another 100 or so galaxies with good rotation curves, and we get an estimate of the Hubble constant of 75.1 kilometers per second per megaparsec. Very recently, Tully's group has done the same thing. They are using line widths, so their method is not as precise, but they have a lot more of them, 10,000 galaxies instead of 100, and they get the same answer. So this is another example of local measurements giving a Hubble constant in the mid-70s, different from the fits to the Planck CMB power spectrum, and this is a real tension, as near as I can tell. And it's not enough to just change the 0-point calibration of the tip of the red giant branch method, because it's in pretty good consistency with the Cepheids. Now, stepping away from rotationally supported systems to a moment, I wanted to note that for elliptical galaxies that are pressure supported, they obey an analogous relation, the Faber-Jackson relation between mass and velocity dispersion instead of the flat velocity, which is usually not measured. So it is a bit of a different relation, but qualitatively it's very similar. And you can see that it extends over a huge range in mass, not just for giant ellipticals, but it extends up to clusters of galaxies and down to dwarfs and even some globular clusters. So that slope, that mass goes as some measure of velocity to the fourth power, works over a really, really wide range in mass, sort of 12 orders of magnitude here. Now, unlike the case for the Tully-Fisher relation, the Faber-Jackson relation is just one projection of a more of a tighter relation known as the fundamental plane. You can see that equation there. I've given some fit from a work by Joachim et al. Including the effective radius as another fit parameter basically gives you a third axis, which explains the variation that you can see on how some of these galaxies, how clusters peel away from this. The radius matters in this sense. Going back to rotating galaxies, that's not true. The baryonic Tully-Fisher relation is already the fundamental plane of rotating galaxies. There is no second parameter dependence. In some sense, we're already looking at the fundamental plane edge on. So what's shown here is the residuals from Tully-Fisher and from the size-mass relation. So you can see galaxies have a wide variation in size at a fixed mass, but no variation in velocity. They're all on the same Tully-Fisher relation, which is nice empirically, but it's weird too, theoretically, because Newton said v squared goes as gm over r, which predicts that dotted line. That is, you have an important component of the mass, the baryons. By construction, they extend over a different radii in these different galaxies, and yet there's just no hint of that on the Tully-Fisher relation. So let's look at Tully-Fisher pair. This is NGC 2403, which is a high surface brightness spiral, and UGC 128, which is a low surface brightness galaxy of approximately the same mass. So they're illustrated here at the same physical scale. The low surface brightness galaxy is much more extended, much more spread out, because it needs that extra area to make up for its lower surface density to add up to the same mass. So since they're the same baryonic mass, they have the same flat rotation. You can see that flat rotation speed there, the orange lines, they're the same to within the uncertainties. But the rotation curves are different. The rotation curve of the high surface brightness galaxy rises faster, as you would expect from the mass being more dense. For the low surface brightness galaxy, it rises more gradually, again reflective of that mass model, the lines shown there. You would expect the peak of the rotation curve to be lower for the low surface brightness galaxy, but it's not. And so it's weird in that it starts out at small radius knowing very well about the baryon distribution, but then it kind of forgets where it goes flat. But there's more to it than that. If you plot the rotation curves, not in terms of physical distance as done here, but in terms of scale length, so you basically divide out that exponential scale length of those two different disks, then the rotation curves fall practically on top of each other. They're more or less indistinguishable. So in physical radii, you can easily tell the difference. In terms of disk scale length, they're basically the same. And so the dynamics, whatever's going on, does know about the distribution of the light and not just its total amount, as you might infer from Tully-Fisher. So there's more to it than that. And this you can see again by eye, that the surface brightness is predictive of the shape of the rotation curve. Tully-Fisher really only tells you about that integrated outer bit. So what about the inner parts, where you can clearly see that the rotation curve is rising slowly for low surface brightness galaxies and rapidly for high surface brightness galaxies? We've quantified this in terms of the central density relation. This was something that Erwin de Block and I noted back in the mid-90s. It's been confirmed many times. Federico Lelli noticed it independently, and we got together and made this plot where we're plotting on the y-axis the dynamical surface density, i.e. what the disk surface density is in terms of mass according to the dynamics measured from the gradient of the rotation curve due to a formula from Toomre going back almost 60 years. And on the x-axis on the left is the central surface brightness. So basically it's surface mass density plotted against central surface brightness. So that's a measure of the central mass density of the stars, whereas the dynamical mass surface density is everything: stars, gas, dark matter. And it is the surface brightness that matters here. It also correlates with the total mass, but that correlation has a lot more scatter, and it's entirely due to the fact that the mass correlates with the surface brightness. So the fundamental relation is on the left. And there, again, the light is very predictive of the mass. At high surface brightness, you don't really need any dark matter. What you see is what you get. That's equivalent to the bulge regions of many galaxies, like we saw in NGC 69946. Just all the mass is in that very high surface brightness bulge. There could be dark matter there, but it's a very small fraction. As you go to lower surface brightness, this ceases to be true, and there's a systematic deviation from the one-to-one line. So you need something extra in low surface brightness galaxies. This is the origin of the statement that low surface brightness galaxies are dark matter dominated, as we noticed in the mid-90s. And it's systematic. The lower in surface brightness you go, the more you need dark matter. The mass discrepancy increases as the surface brightness decreases. Now, going back to our Tully-Fisher pair, galaxies of the same mass but different surface brightness, you can see how on the right they basically line up the same mass very nearly, whereas on the left they're in very different locations. And this is all very systematic. You can predict pretty much everything about the shape of the rotation curve just from the shape of the light distribution. So what about everything in between there? So here's one galaxy, the surface brightness profile on the top. This is what we use to solve the Poisson equation to predict what the rotation curve for that mass component of stars should be. And so we get that baryonic rotation curve in blue on the bottom. And then the observed rotation curve is just that gray band there, those black points. And that is just the centripetal acceleration that one actually observes. And those two things are tightly coupled. So here are now a few examples, a bulge-dominated spiral on the left, a sort of disk-dominated spiral in the middle, and then a gas-dominated dwarf on the right. You can see their mass models are very different. The bulge-dominated spiral, basically, it explains the inner few rotation curve points. It's just the bulge, but after that, you need something else. The spiral is about the same, but not quite maximal in the center. And then the gas-dominated dwarf, basically the baryons don't explain the rotation curve anywhere. That is, even near the center of the galaxy, you need some dark matter. Now one can also plot this in terms of the accelerations. So the bottom row of panels shows the centripetal acceleration that's observed in the rotation curve as a function of what's predicted by the baryons. And so in that left panel, you get the black line. That's basically the ratio of the data to the blue line in the panel above it. And then that's kept in the middle panel as the gray line. You can add on a new black line. And then do that again for the dwarf. And you see that they're all following more or less the same trend in that diagram. So we can just plot all the data together. This is now a heat diagram for 153 galaxies, nearly 2,700 independent points. And you cannot really distinguish individual rotation curves in this diagram. They all fall on top of each other within the uncertainties. And so this is a remarkable thing. There's no reason that all these very different rotation curves, all these very different morphologies should give you such an orderly result, but they do. So orderly that you can bin up the data, those are the red squares, and fit a line to them, and that's that function on the left. The observed acceleration is a function of the baryonic acceleration. So if you know one, you know the other. Remember that baryonic acceleration we obtain from solving the Poisson equation as applied to the mass distribution that we can see. So the total mass distribution that includes dark matter is strongly coupled to the distribution of baryons, even in systems where the dark matter is completely dominated. And in fact, the scatter here is basically consistent with what you expect from known sources of uncertainty. There are, of course, a few weird cases at high deviation, but the vast majority of the data all fall along this line. So again, this relation, like Tolley Fisher before it, is consistent with being essentially zero intrinsic scatter. Again, stepping aside and looking at elliptical galaxies, pressure-supported systems seem to follow a similar trend. So there are giant ellipticals in both red and orange, measured in different ways on the right. And then extending down to the dwarf spheroidals of the local group, where things get really noisy. I think most of that is, again, a data quality issue. You can see the size of the error bars. But on top of that, many of these things are little tiny dwarfs up close to a great big host galaxy like the Milky Way or Andromeda. So you have to worry about tidal effects disturbing them from their dynamical equilibrium. So I don't put too much stock in that, other than that the broad trend continues and seems to apply to both pressure-supported and rotationally supported systems. Now, it's really an amazing thing that the what you see is predictive of what you get. You can take that radial acceleration relation, you can apply it to the observed distribution of baryons to predict the rotation curve. So that's what's shown here is that black line that is the declining predicted rotation curves of the baryons can be amplified by that formula left to give you the blue line that goes right through the data in considerable detail. As you go to larger and larger radii in galaxy, you're going to lower and lower acceleration because the acceleration goes as v squared over r. So the correction factor from that formula gets bigger and bigger as you go further out and gives you that flat rotation curve. But it also preserves the good fit to the inner part of the rotation curve that was predicted by the baryons in the first place. This also works in low surface brightness galaxies and even to the point of mapping those features that Rinzos and Chisi noted from the baryonic distribution to the total rotation curve. And this works despite the fact that the baryons are subdominant everywhere. It should be just the dark matter halo, and yet the shape of the predicted baryon rotation curve maps very nicely into the total rotation curve. Now we can do this a lot. My most recent graduate student, Pingfei Lei, just graduated and made fits of this kind to all of the galaxies in our Spark sample, 170 some of this sort. So basically the mass to light ratio is the one unavoidable physical parameter. You don't know what that is a priori, so you have to fit for that. In a Bayesian sense, you can control for nuisance parameters like the distance and the inclination. Pingfei has done all of that and gives you fits like this for a more typical quality data. You can see that's a very good fit. The mass to light ratio is a little higher than we had originally assumed, but within the scatter of what you'd expect. I would note here the chi-squared is large. If you look close, you see the error bars are tiny, and that misses in a few places where the fit is, so chi-squared makes you pay the penalty for that. So if all you did was look at chi-squared, you would say this is a terrible fit and reject it. If you use your eye and your brain, you look at that and say, well, that's a good fit, and probably error bars are underestimated because there is no physical model that will go through all those points with the error bars as shown. They're too small. And I mention that because there are a lot of papers in the literature these days claiming, oh, God, this doesn't work at 10 sigma or whatever, and that is simply based on a misunderstanding of astronomical uncertainties. There's always a large amount of uncertainty in the uncertainties in astronomical data, especially rotation curves, where the formal error bars here are clearly underestimated. There are other examples where they're overestimated. And so chi-squared is indicative, but not definitive. You can't trust it all that much. If you went and made other kinds of fits with dark matter halos, which Pingfei has also done, then what you find is the same line over and over again. This is what a fitting program finds as the best guess to go through all those data points. You might get incremental improvements in chi-square. Maybe it's 4.8 instead of 4.9, but it's bad any way you do it. So there is no model that can explain all the data with chi-squared of 1. That is an indication that the error bars are underestimated. Now we can do this, as Pingfei has, over and over and over again for all these galaxies. So I'm going to show you a whole bunch of fits, and I'll just skip through them pretty quickly. The gray bands give you some idea of the uncertainty of what's essentially the prediction of going from the baryonic mass model, shown as the dashed and dotted lines, to the total rotation curve fit, which you can do over and over again for all sorts of galaxies. And you do see some weird cases. F579 V1 at the right, bottom right almost, is not quite perfect. If you look in detail at that case, it's lopsided. one side of the rotation curve rises much more quickly than the other side. So what do you take as the circular velocity? We don't really know. And so you shouldn't be surprised of a misfit in cases like this. And this goes on and on and on and on. We can make all sorts of fits over and over to really high quality. And most of them work, as I say, like DDO 168 in the bottom right corner. There's the occasional misfit in GC 2915, and sort of the middle right is the case that bothers me most. But it is one case out of hundreds, literally, that just work right. So there is something systematic going on that we need to understand. And in fact, you can ask, how well can you do the prediction without any fitting at all? That's done on the left. All I've done is plot the residual diagram, the ratio of the observed to the velocity predicted, just by applying the radial acceleration relation to the observed light distribution for the assumed mass to light ratio that I told you before, 0.5 for disks and 0.7 for the bulges. And you can see that mass to light ratio on the bottom as a function of the effective surface brightness, and it's just a line except for a few cases that have bulges. And of course that's wrong, but nonetheless it does pretty well in predicting the rotation curve. Now if you let yourself do the fit and adjust the mass to light ratio that's shown on the right, then of course the fits become better. They are best for the best data, and you get scatter in the mass to light ratio, which you know from a population perspective has to be there. And in fact, the amount of scatter is reasonable compared to models, which predict something like 1/10 to 2/10 of a dex in scatter there. What we observe is about 0.11. So, you know, this works as well as it could possibly be expected to. So this is really key, and I started out calling these kinematic scaling relations, but I think they're more laws of galactic rotation in analogy with Kepler's laws of planetary motion. Rotation curves become flat if you observe far enough out. That happens every time we've been able to look far enough out. Any case where there was some question to that pretty much goes away when you extend the data further out. Rinzo's rule applies wherever we see it. In 90% of the cases in the spark sample I just showed you, there's no question about it. In a few cases, the features are there, but just a little bit offset. But that's only 10% of the cases, you know. Baryonic Tully-Fisher relation is just absolute. Everything that rotates falls along it. Every galaxy anyway. The central density relation is at this point well established, been known for a long time. And these things are all tied together by this radial acceleration relation. That is, the accelerations that are observed in the kinematics is predictable from the distribution of the baryons that Newton tells us, just with the boost that's given by this formula. Now, I'm going to add one last thing, that all of these kinematic relations involve a critical acceleration scale. In the radial acceleration scale, that was the fit parameter, and is about 1.2 angstroms per second per second. That tiny scale is the typical centripetal acceleration in a spiral galaxy. But you get that out of Tully-Fisher and the central density relation as well. So in the case of Tully-Fisher, you can rearrange the axes. It's basically the fourth power velocity divided by Newton's constant times the mass has units of acceleration. And so that line seen at right, that is a line of constant acceleration. It's not been fit, that is just a line of slope 4. And so you can define a characteristic acceleration for each galaxy, and the mean of that gives you an acceleration with some scatter. It is basically the amount of scatter that you expect from the uncertainties. And that number is consistent within the uncertainties with the acceleration that one fits in the radial acceleration relation. Similarly, for the central density relation, there is a bend at a particular surface density, just shy of 1,000 solar masses per square parsec. You can relate that surface density to an acceleration by multiplying by Newton's constant. And again, if you do that, you get that that bend occurs in the same place as it did for the radial acceleration relation. So each of these relations codify a critical acceleration that didn't have to be the same. It didn't have to be there at all. And yet they all point to the same number within the uncertainties. So there is something special about this acceleration scale. Here I've shown gravitating systems over 25 decades in acceleration at the high end. Sort of the highest acceleration one can conceive is the surface gravity of a neutron star that's on the brink of collapse to a black hole. We have measured directly the final orbit of the merging black hole. This is the first one detected, is listed there at about 10 to the 11 meters per second. Gravity works fine there and all the way down to much smaller scales all through the solar system. Each of the planets is marked there. Pioneer 10 is even marked, including its alleged discrepancy, which is so small on the scale that you cannot perceive it. But as you go to lower and lower accelerations, when you get down to this critical scale of about 1 angstrom per second, that is where you infer the need for dark matter, both in galaxies and with a slight offset for clusters of galaxies. So that's where things happen, and that scale is critical to understanding the missing mass problem. So I have reviewed some of the photometric scaling relations that we know about for galaxies. These are not particularly strong. There's a lot of scatter and depend a bit on how you define them. In contrast, kinematic scaling relations are very strong, having very little intrinsic scatter. For example, if you know the mass of a galaxy, you know how fast it's going to spin. That's Tully Fisher. And these kinematic scaling relations share this common acceleration scale, and understanding why that happens is key to deciphering the dark matter problem. Thank you for your attention. I hope this recording went well. It's kind of strange to talk to a screen instead of an audience, so I wish you all the best, and thanks for listening.
Wrote all the questions, and I will answer some of the question, and some of the others I think Professor McGaugh will answer more details. Okay, wait, one more question. First, I will answer for Suzu. In gas and stellar part, how to measure the mass of gas and stellar individually. Okay, for gas is you have to measure the hydrogen neutral using the 21 centimeter spectra line from radio, and there is a relation between the density, the column density of the gas, and relate to the distance and the dimensions of the galaxy, and you can determine the mass, the total mass of the gas in that galaxy. And also the stellar individually, Professor McGaugh already explained in one of the slides that you need the mass to light ratio. What you observe is only surface density, surface brightness. So the brightness, you need the mass to light ratio to change from the luminosity to the density. From density, you have the dimensions of the galaxy, and you can measure the total mass of the of stars, of stars. And the next from Bhuvaneswari, does accounts the baryonic mass? Yes, of course, but the fraction of gas is very small compared to the hydrogen mass. So you need the baryonic mass is stars and gas, and but the gas fraction compared to the gas is very small. So you can include the fractions to the gas mass. Second, Sharif Faris, in your presentation, you show importance of the data you choose to create the plot. Have you ever found an instance where it's useful to use less data, like a detail that you miss, if you use the whole database, or is more data always better? I think this question I will send to the Professor McGaugh. He can answer. Also from Arif Nurrahman, how Professor successfully predicted the velocity dispersion of many of the dwarf satellite galaxy of Andromeda, why television is fundamentally different. I think this question also uh, Professor McGaugh will answer. I will send you the answer. Uh, from Naman S. Bajaj, what are the possible explanations of television relation? Is any one of these more accepted than the others? Uh, yeah, this more detail about the physics or the detail of the television. I think Professor Mika will answer it. From Muhammad Rafif Rabani, in principle, how does one construct the selection function to account for the selection effect? Do you expect scaling relation to vary with relative? I think I will send to Professor Mika. So from Bhuvaneswari, Kasi, everyone, does the mass of galaxy include the mass of the black hole in the galaxy? I will answer. The mass of the black holes in the center of galaxy or supermassive black holes is between 10 to until 10 to the 8 solar mass. But the mass of a galaxy is order of 10 to 10 or to the 12 solar mass. So it's very small compared to the mass of the baryonic and all. So it's included already. Uh, from and then from question from Muhammad Irfan from Bosha Observatory, how do elliptical galaxy rotates? Stacy explained that there are two types galaxy pressure supported, like the elliptical galaxy, and also rotation supported galaxy. Rotation supported like a spiral galaxy on some also Magellanic clouds. How the elliptical galaxy rotates, I think we cannot. Stars are the orbit as irregular, yeah, randomly regular. So the distribution become a spheroid. I think so, but I think so because this is also related to the from Muhammad Hassan Zaki bin Yusuf. Does the rotation curve method can only be applied to a spiral galaxy or also apply to the regular galaxy? The rotation curve method we can observe from the spiral and some of the irregular galaxy, but the elliptical galaxy we cannot observe the rotation. We measure only the velocity dispersion uh, from the spectra of the galaxy. Uh, okay, then uh, from Emil Shahreza Fadila, does the equation relating to G ops and G bar implies direct relation between the baryonic mass and distribution and dark matter distribution? I think so, because it's more simple way. You don't model from G op measure the uh, square of velocity square divide by r, the distance from the center. You measure from the distribution of the gas or uh, total gas and stars from the, and you have this and tends to the density. You can derive the G bar or its uh, force. baryonic. It's so you have the difference. The difference is related to the dark matter contributions, but not the dark matter distribution. How it distributes, you cannot measure, but you can relate it to the in certain distance. There's variations. I think. And the last one from Salma Zahra Fadia, does the inclination of galaxy affect the measurement of kinematic scaling relations? Yeah, you have to find the inclinations, and also but usually if you measure the distance and rotations, you have to also correct for inclinations of the galaxy, so you can measure the rotation velocity better in yeah, effectively, something like that, because in some inclination you have to correct the inclination, and you have to like the edge on to measure the rotation curve and other kinetic. I think that's all the question. Oh, one more questions. Oh, there's other question. Okay. Can we derive from Muhammad Rafif Rabani? I think. Sorry. Yeah, can we derive predict a scaling relation by modeling? Okay, I will send to Professor. Actually, principle, the questions here in the chat will be sent to Professor Stacy McGaugh. I will answer only for the short and the easiest one for me to answer. And Rafi Adnan, can we apply any form of kinematic scaling relation for irregular or elliptical galaxy? No, scaling relations like a Tally Fisher related only for spiral galaxy, and Faber Jackson only for elliptical galaxy. You cannot mix anything, but there's some, yeah, but if most of the general, I think it relates in any dark matter, but yeah, in principle, there are two types from Tally Fisher and Faber Jackson. It's different from galaxy type. By default, we will send all your questions. Yes. Does the kinematic scaling relation explain the mass of the dark matter halos from Lee, or do we need something like dynamic scaling relations? I think I will, yeah, send to Professor McGaugh to answer these questions. Okay. Thank you very much for participation here, and also all questions, very good questions. All these questions will be sent to Professor McGaugh, and I hope he will answer more clearly than my answers, of course. Okay, then, Anton, the last one, we take a photo session, right?
Yes.
Okay.
Please, I wanna invite you all to turn your videos on. Okay, please, for another participants. Okay, by default, every the end of the lectures, we will take a photo. Please prepare yourself. Okay. Okay, for the first slide, I will try to take the photo first. Okay, 1, 2, 3. Okay, and go to the next slide. Okay. Wait a minute. Okay, 1, 2, 3. Okay, thanks everyone.
Okay, you're welcome.
Thank you, Sir Professor Iqbal.
Yeah, you're welcome. Thank you.